For last couple of classes, we have been discussing extensively about analysis of the proton and NMR spectra of different types of molecules, where I told you sometimes the types of tricks that you have to adapt in looking at the pattern and making the assignments. You may have to look at the intensity, you may have to look at the chemical shell position, you have to look at the multiplicity pattern, sometimes you have to measure the frequency separations. All those tricks you have to adapt and then make a assignment of each peak to the particular protons in a molecule. That is the basis is required for the utility of NMR spectrum. First thing you have to make is the assignment of all the peaks, and this is how we started the analysis. And before I end this analysis of the proton spectrum, in the last class I gave an example where there was a fluorine coupling. I'll continue with this. With a proton can experience simultaneously coupling with multiple heteronuclei. I'll show that example and also discuss about sometimes it may appear to you that peak is missing. It may not be missing. It will be still present there, but you should know how to extract it. Like that, one or two examples I give, and then we'll go to carbon-13 number. Let us look at the spectrum of this molecule: CH3, CH2, SpF2. Now, observable NMR nuclei for detecting, we have three here. I'm not bothered about the sulfur. I'm looking for phosphorus, fluorine, and proton. All the three I'm seeing. I have a CH3 group, I have CH2 group. Forget about sulfur, but it is in the molecule. I have phosphorus and fluorine. As far as I am concerned, there are 1, 2, and 3 abundant heteronuclei. Remember, abundant. All this coupling can be clearly seen in the spectrum. Of course, this is NMR active, this is NMR active. They are less abundant, carbon-13, so you will see them as satellites. So we will not worry about satellite analysis at the moment. Right now, let us concentrate on analyzing the proton spectrum of this molecule. When I see proton, I get essentially two groups. One for CH3, other for CH2. Of course, that is very clear. And now, the CH3 comes where? In the high field region. That's also clear. And CH2 comes in the low field region. That's also correct. Now, this CH3 has to be a triplet because of CH2. That also we have been utilizing this idea for quite some time. So it is a triplet. But each layer of the triplet is additionally a triplet. How is it possible? This can happen only when the CH3 can have a long range coupling with fluorine. So this is 1, 2, 3, 4, 5 bond coupling. 5 bond coupling with this CH3 protons and 2 fluorines which are equivalent gives rise to triplet of triplets. Remember, this is magnetically equivalent. You apply 2Na+1 rule. Then triplet of this, because of this CH2, it is triplet, and now because of F2, each lane of this triplet is an additional triplet. So this is a triplet of triplets you are going to get. Then you may ask me a question. Phosphorus is 100% abundant. That is also spin-off nuclei. Where is that coupling? See, this 4 bond phosphorus fluorine coupling is very weak. Hence, as a consequence, you are not seeing it here. Okay, otherwise, it would have even complicated much more. This 9-lane pattern would have become 18-lane pattern because each of them would have further split into doublet because of this phosphorus. So we are not seeing that coupling. So it is only triplet of triplets. Now coming to CH2, it is very interesting. What type of coupling pattern you expect for CH2? First thing, CH2 can couple to CH3. It's a quadret, very clear. But this can also couple to phosphorus. It is 1, 2, and 3 bond coupling. It is present. 3 bond phosphorus proton coupling is reasonably good value, 8 Hz. Only 4 bond coupling we didn't see here. That's all. 3 bond coupling is there. In addition to that, this CH2 protons can also experience coupling with 2 equivalent fluorines. So it experiences coupling with protons, phosphorus, and fluorine, all the 3. It's a very interesting example. That's why I wanted to show you A proton simultaneously experiences coupling with three different heteronuclear spins. And in the very first example, when I was giving you salient points of scalar coupling, you remember I said each nuclei can experience multiple heteronuclear couplings at the same time. It's a classic example now. The CH2 is experiencing coupling with proton, phosphorus, and fluorine, all the three. Once you know that, its analysis becomes fairly simple. Now, first thing is CH3 coupling is a big quartet, and this large coupling is about 7 hertz. Interestingly, 3J HB coupling is much larger. So this will be first a doublet. And then each line of the doublet will be split into a quartet because of this. You will get 8-line pattern. And each line of this is going to be a triplet because of this F2, chemically equivalent fluorine. So that's what you are seeing. It is a doublet of quartets of a triplet. You can see 1, 2, 3, 1, 3, 3, 1, 1 quartet, 1, 3, 3, 1, 1 quartet, 2 quartets. And center of this quartet to center of this quartet correspond to doublet. And each of these line is a triplet. See, with many overlaps, you are not seeing all the lines carefully, but you can see very easily, you can understand. First doublet is from center of this to center of this, and now the quartet comes because of CH3 1 3 3 1 1 quartet, 1 3 3 1 another quartet overlapped, and each line of this is a triplet, which you can clearly see very nicely. All multiple nuclear heteronuclear couplings can easily be extracted from this. But remember, don't expect coupling between phosphorus and fluorine here. It may be present, but you will not see. Remember, you know why I am telling you? I told you long back, this is an active spin when I am seeing that. And this is passive, this is passive, this is passive. At the site of the active chemical shift, you will see coupling between active spins and passive spins. That's what you are seeing here. Coupling among the passive spins like P, F and CH3, you will not see because they are passive couplings. Okay, that is why you see only coupling of this to this, this and nothing else. And that is where you can analyze. And another simple molecule you see. This is 3-fluoropropanol. Now, this is fluorine is present. This is CH2, 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 OH. Very easy. When it is coupled to CH2 with this fluorine, then what will happen? This CH2 has to be a doublet because of this. And then it is also coupled to CH2. It will become a doublet of triplets. But remember, 1-bond FH coupling is quite larger compared to 2-bond, and this is larger compared to 3-bond. I will give you the coupling values. 1-bond fluorine proton coupling is 45 hertz. Now, which is that you can see a large doublet, and each line of the doublet must be a triplet. Where do you see that spectrum here? Look at this. This is a bunch. A large doublet, each line of the doublet is a triplet. Then this has to be proton 3. Also, it is attached to electronegative atom, so it comes downfield. That is another way. But I am assigning based on the coupling strength now. And what about this one? This is 2-bond couplings between the 1, 2 and 3-bond couplings will be 24 hertz. Look at this one. Where is that? This one will be a doublet because of this. Each line of the doublet is split into triplet because of this, and another triplet because of this. Very complex pattern. So that means it will be a quintet or a septet, whatever it is. 2 such patterns should be there. So it will be a doublet of sextet or septet. Where can you see that? It is here. The expanded portion of that, if you see, you get 1, 3 pattern here. See, it is a pentet-like pattern. This is a pentet-like pattern. Center of this to center of this correspond to a doublet, and each die of the doublet is split into this CH2 and this CH2 gives rise to a pentate pattern. See, this is 131 triplet, 131 triplet, 131 triplet. So overlapping, giving rise to a pentate. So this is also assignable. This corresponds to proton 2. Then what is proton 1? Proton 1 is far away and long range coupling to fluorine is 0 to 3 Hz. Sometimes you may not get it resolved. You may not be able to see that. No problem. Then it is coupled only to the CH2 which is neighbor to 8. As a consequence, proton 1 is a triplet. So assignments based on the coupling strength you can make easy. This simple analysis of a molecule heteronuclear based on the heteronuclear coupling strength you can also do. Sometimes you come across a situation like this. It is a very simple molecule I have taken. CH3, CH2, CH2, CH2OH. N-butanol. It is done in CdCl3. CH3, is a triplet because of this. This CH2 is a quartet and a triplet, a complex pattern somewhere here. And this CH2 is a triplet of a triplet because of these two somewhere here. And this is a triplet because of this one that is here. Now my question is, we have 5 groups of protons including OH. Where did that OH go? My question is, I assign this 1, 4, 2, 3. Now the question is, where is OH? It must be there somewhere in the spectrum. Sometimes what happens, OH piece is obscured by the multiplet at 1.39 ppm. What is that multiplet at 1.39? This one. See, OH is hidden here. Look at it. You can see a broad OH peak is below this. OH peak gets broadened. In addition to that, it is hidden below this peak. It gets obscured. Then how do you know it is OH? How do you get that out? You will not get it out at least. You must be able to say this is OH peak is there. How do you do that? There are certain tricks adapted for this. The trick is take a small amount of less than 10 mg or 15 mg of D2, less than a small micro drop, 1 drop of D2. You add to the solution in NMR tube. Shake it for some time. Add 1 drop, shake the NMR tube for some time. Sometimes, depending upon the exchange rate, it may go fast, or sometimes after 2-3 minutes or 5 minutes, or sometimes half an hour, no problem. Then record the spectrum after some time. Look, this became a very clear pattern now compared to this. Earlier, you see, it was OH peak was obscured by this bunch. Now that OH disappeared. You get very clear multiplicity pattern here. What happened to OH then? When you add D2O, OH will become OD. It is not protonated anymore. It is deuterated. Because it is deuterated, you don't see the proton spectrum. As a consequence, OH peak is not seen. But at least you identified OH was hidden here. So these are some of the tricks of the trade you should know, looking at the spectrum, where to identify OH, where it is hidden, and based on the coupling strength, how to analyze. Now I took an example today where one proton can experience coupling with 3 different nuclei, proton, fluorine, phosphorus, like that. And how do we get the coupling information? How to analyze the spectrum? I showed all those things. So I hope you all have the idea of what to do everything. And of course, NMR is a big ocean. If you start analyzing large number of spectra, we can do, right? So this is a reasonably small molecule to small complex molecules I have taken. Go to bigger molecule. Real experts go and start analyzing the spectrum of proteins. Very big macromolecules also. That comes like a bit of experience. Once you start doing this work, it is a matter of time. In a few months, you will become an expert to analyze even the complex molecule. So with that, I will stop about the analysis of proton spectrum. Now I will go to the other one, that is analysis of the carbon-13 spectrum. I will start another nuclei. We will start here afterwards analysis of the carbon-13 spectrum. Why I took carbon-13? Because for the chemists, especially organic chemists, carbon-13 is another extensively utilized NMR nuclei. Because all your molecules contains carbon. I am not talking about inorganic chemists. They also have different exotic nuclei. We will come to that later when we do other multinuclear NMR. Now I am concentrating on carbon-13. Generally, most of the organic chemists come to us and say, I want carbon 13 NMR. Because they synthesize the molecule, they want to see proton NMR and carbon 13 NMR. So after proton, especially for the chemists, this is second most sought after nuclei. Some important points about carbon 13. Carbon 13 has two naturally occurring isotopes, C12 and C13. C14 is also there, but that is radioactive. Ignore it. It's unstable. We concentrate only on carbon 12 and carbon 13. If you remember the very first class, when we worked out the spin of the nuclei, I said carbon 12, because of the even atomic mass and even atomic number, 12 and 6, its spin is 0. That's what I said. So when spin is 0, magnetic moment is 0. When magnetic moment is 0, there is no interaction of the magnetic moment with the external magnetic field. So no Zeeman effect, no splitting of energy levels, no NMR. That's what I said. The spin is 0, such nuclear NMR inactive. So carbon 12 is NMR inactive. Interestingly, this has 98.9% abundant. 98.9% abundant. And carbon 13 is only 1.1% abundant. You see this thing? Supposing, it is nature is helping us. You should take it as an advantage for us. If carbon 12 were to be 100%, let us say, abundance is 100%. In all the organic molecules, you have so many carbons. Your spectrum would have been so complex, NMR spectrum, it would have been impossible for us to analyze easily. We had to struggle a lot and to get analysis of this because it used to couple with all protons, proton-proton coupling, proton-carbon coupling, carbon-carbon coupling, everything would have been there. Fortunately, nature is helping us. As a consequence, we don't see carbon 12 at all because they are NMR inactive, and we concentrate only on carbon 13. Interestingly, it is also very good for us because it's a spin-half nuclei. I told you, remember, spin-half nuclei are relatively easy to study compared to nuclei spin greater than half. Okay. When do you make use of carbon 13 NMR? Look for proton NMR. If I have a CO group, C double bond C, C triple bond CN, or CN group like that, if I want to get information about such type of groups present in a molecule, proton NMR cannot give you. Where is the chance for proton NMR to give that information? There are no protons here. On the other hand, I can study carbon here, I can get this. I can study carbon and all these functional groups present can be identified. So carbon 13 NMR is also very useful. Whatever sometimes information which you cannot get for certain functional groups in the proton NMR, you can get from carbon NMR. Okay. And now salient points you should also remember when you are analyzing the carbon 13 spectrum. Remember the factor which affects the chemical state of proton also affects the chemical state of carbon 13. Same. There is no difference. Similarly, if I say CH3 proton is coming high field, CH3 carbon is coming high field. If I say next comes CH2 proton, CH2 carbon also comes there. By and large, it follows the trend. More or less, it follows the trend. So the factors that affect the chemical state of protons also affect the chemical states of carbon 13. Next question is, I told you when I used the reference as TMS, this TMS has tetramethylserine, has carbons, protons and silicon. As I said, there are 4 carbons, all are chemically equivalent here. And I said it's a very good reference for carbon 13 NMR. So the reference used for carbon 13 is again TMS, like what we use in proton. Resonating frequency of carbon is 4 times less than that of proton. I hope you don't have to ask me questions. I hope you know the answer why. The reason is gyromagnetic ratio of carbon is 4 times less than that of protons. As a consequence, resonating frequency is 4 times less. Of course, it also means sensitivity is 4 times less. We'll come to that later. Now, if you look at the chemical shift range of carbon 13, again it is measured with reference to TMS. Proton is 0 to 10 ppm, but carbon is 0 to 300 ppm. Very interesting. Remember, if I have a 500 megahertz spectrometer, if I want to study proton, 10 ppm. So I will cover only 10 into 500, 5000 hertz. That's all my range of observation. That is the width of spectrum I want to see, called spectral width. If I have to see the carbon 13 in the same 500 megahertz, is 125 megahertz is the carbon. Now 125 into 3, 125 into 3, it is 37,500. It becomes huge. Spectral becomes quite large, you know. So this is what the important point you have to remember when you are looking for proton and carbon. Another point is, most of the time carbon 13 spectra are obtained with broadband proton decoupled. You may be wondering, what is this decoupling? I have not introduced it yet. I will introduce to you later. But please remember, in the case of carbon 13, we break the coupling of all carbons to all protons. Then what will happen? We will see later. When there is no coupling to all carbons, will become single lines. Carbon-carbon coupling we don't see, only carbon-proton coupling. That we remove. When we remove that, you get only individual carbons, individual peaks. And each peak then can be identified for individual carbons. So in a carbon 13 spectrum, you take a proton decoupled, broadband decoupled carbon 13 spectrum. If I have a molecule with 5 different carbons, you will get only 5 peaks. Very simple, 1 1 1 1 line, no multiplicity. 1 1 1 1 line, you get 5 lines. If I have a molecule with 10 carbons, do proton decoupled carbon 13 spectrum you take, you get only 10 peaks. That's all. Easy to understand. No breakage effect. Analysis of the carbon spectrum is much easier than that of the proton. Okay. But you took the example of phosphorus fluorine coupled spectrum we saw in the proton, you know, just few minutes before. There we had a phosphorus and fluorine, Ca3 and CH2 group. If I take carbon 13 spectrum of it, you will remove carbon proton couplings. But what about phosphorus fluorine? No, that you don't remove. See, remember, very interesting thing about NMR is selectively you can break the coupling of one nuclei with other, but other heteronuclear coupling you can retain also. That's a very interesting thing, you know. If I have, let us, nowadays with the present day spectrometers, you can do decoupling of one spin, one nuclei, two nuclei simultaneously like that. Many things is possible. So I can decouple one nuclei at a time. All protons can be decoupled with carbon. I can get proton fluorine and carbon fluorine, phosphorus carbon, all couplings I can see. Very interesting. So select, or I want to retain carbon proton couplings. I want to remove fluorine couplings. I will remove fluorine couplings. It's possible. I can play with it. This is the beauty of NMR. I can play with the nuclei. I can remove the coupling of the specific nuclei and observe that. So that is what broadband decoupling of heteronuclei. I'll come to that later. Another interesting point you must know is the magnetic moment of carbon 13 is relatively 4 times less than that of proton. That is because Gaussian magnetic ratio is 4 times less. I told you. Gamma of proton I said 26.75 into 10 to the power of 7. Similarly, carbon is 6.7 to 10 to the power of 7. I told you radians per Tesla per second. There must be radians here. Okay, it is expressed in radians. What does it mean? Gamma is 4 times less means in the very first class in spin physics we discussed. That means energy states of carbon is 4 times smaller than that of proton. Okay. Now this is the energy separation of carbon, and this is the energy this is the energy separation of proton. This is 4 times less. Remember I said this is also spin half nuclei. Okay, this also has 2 possible orientations, alpha beta, but this is less sensitive compared to this because of less gamma, and energy separation is 4 times smaller. I told you about sensitivity when we discussed. The sensitivity depends upon magnetic field, which in turn is responsible for this energy separation. As a consequence, carbon 13 is less sensitive compared to proton. Okay, so in a 800 megahertz spectrometer I will take, if I say proton comes at 800, where does carbon come? If proton comes at 800 megahertz, carbon comes at 200 megahertz. You understand this very clearly. Now, I told you about the sensitivity of the nuclei, gamma cube, everything I discussed. I don't think I have to go again. Sensitivity of the nuclei depends upon three factors I said: population difference and magnetic flux and magnetic moment, all are proportional to gamma. I said it is gamma cube. Remember, you worked out the sensitivity for proton, carbon and nitrogen related to that of proton in one of the classes I showed in the slide. I guess you remember all those things, right? Don't forget that sensitivity factor we calculated. Again, I'm showing it here. Sensitivity of the carbon-13 related to proton, when you take only gamma cube into account, it is 63, almost 64 times. Okay. Whereas if I look at this sensitivity, taking into account abundance also, we saw it is 5672, nearly 5700 times less sensitive than that of proton. So it is 5672 times less sensitive means if I have to get the signal to noise ratio comparable to proton, we need to acquire 5672 to 5672 number of scans. Okay, because signal to noise ratio goes by root of square. It takes enormous amount of time. So carbon-13 NMR is more time consuming than proton. So this is the situation. This is 567. Let us say in one scan, one accumulation. When I send one RF pulse, I'll get a proton spectrum of particular signal to noise ratio. For the same signal to noise ratio, if I have to get the carbon-13, taking sensitivity, gamma, and abundance into account, I have to acquire this many number of times scans. I have to send that many number of pulses and collect the signal. Of course, further assuming various other parameters are there in NMR like relaxation, etc. are identical. If it is not, it is a different question again. So it doesn't matter. All this tells me the carbon-13 NMR is more time consuming than proton NMR. Understood the point? Carbon-13 NMR is more time consuming than NMR, proton NMR. That's why we keep on adding the data, do signal averaging. I'll tell you what is signal averaging when I come to practical applications, how to get the spectrum, how to process the data, everything I'll discuss in one of the classes. But till then, you keep this point in mind. We have to keep on adding the data. If I send only one pulse and collect the signal, this is the NMR spectrum, carbon-13 spectrum of this molecule. What can you make out of this if I give you the spectrum? It is very difficult, right? So I look at the spectrum with a single pulse, sending one radio frequency pulse. If I collect the carbon-13 spectrum, it looks so noisy. It is very difficult to get any meaningful picture out of this. What can you get out of this? Look at this, many peaks are not even visible. On the other hand, we can do the coding of the data. I can, instead of one pulse, I'll send 10 pulses, one after the other. You send a pulse, collect the signal. And afterwards, send one more pulse, collect the signal. Send one more pulse, collect the signal. And then keep on adding the data every time you collect, one above the other, like this. So it is a one accumulation, we call it as accumulation. Accumulation of the data, one pulse accumulation or signal averaging. So you apply send one pulse, acquire 10 pulse. Now apply 100 times. 1000 pulses you apply. Every time quad the data. What is the change you are seeing? Look at it. It's very noisy. The noise reduces, much less. And you see all these peaks which were not visible here, especially this peak. And look at this signal to noise ratio of this peak. We can clearly see all these peaks. So carbon-13 NMR requires lot of data acquisition. Enormous time it requires compared to proton. I give a simple example. Of course, nowadays things have become better with the high frequency spectrometers and electronics is different. There is a change in electronics. My NMR methodologists are doing the experiment have improved so much. So many sophisticated experiments we can do. We can do faster, no problem. But still, if I take proton spectrum in 1 minute, carbon-13 will take at least 15 minutes to 30 minutes, depending upon the concentration and the number of carbons you have in the molecule. So yes, basically relative to proton, carbon is time consuming. Now I'll introduce a word called isotopomers of molecules. This you would have come across in chemistry. I don't have to explain to you. I'll take the example of CHCl3 chloroform. I'll take 100 molecules. 99 molecules contain carbon 12. That is a major abundant spin, right? Abundant, which is 99%, carbon 12 is abundant. Only one molecule is carbon 13 because its abundance is only 1%. So in 100 molecules, on a statistical average, if I take 19 molecules are carbon 12 attached, which are NMR inactive. C12 is NMR inactive because spin is 0. Whereas C13 is NMR active and spin is half. With this idea, let us see what happens if there are two carbons in the molecule. I consider a situation there are two carbons. How many isotopomers we can think of? There's one possibility. There are two carbons which are bonded. I'm not worried about the complete structure. Just concentrate only on the CC fragment. This carbon can be 12. This carbon can be 12. What is the probability of that? This is 99.8%. This is 99.8%. Together, the probability of both of them carbon 12 is 97.8. NMR inactive. That means if I have 100 molecules present, 98 molecules are with both of them carbon 12. It will not give a spectrum at all. It is NMR inactive. On the other hand, think of this possibility. This is carbon 13. This is carbon 12. It is quite likely. We can see that. What is the abundance of this carbon? Only 1%. And this is 99%. So this is NMR active. What is the other isotope we can think of? This one. This is carbon 12. This is carbon 13. That's also possible. That is also 1.1% abundant and NMR active. So in a molecule containing two carbons, 98% of the molecules contain carbon 12, which do not give us the signal at all. In the carbon signal, it will not get. You will not get carbon signal at all. Only this will give carbon. 1% of this small isotopomer, 1% of this isotopomer will give signal. You may ask me a question. What is the other probability when both are carbon 13? Sure. Both are NMR active. Now, what is the abundance of this? This is 1%, 1 in 100. This is 1 in 100. Together, the joint probability is always a product. 1 over 100 into 1 over 100, 1 over 10,000. So this is 0.0012%. In 100 molecules, probability of seeing this is almost 0. You will not see that. Although NMR active, you will not see that. So probability is 1 in 10,000. Extremely difficult to detect molecules, isotope with both carbon in carbon 13 state. Okay, that's fine. Now I will go to carbon 13 with 3 molecules. There are 3 carbons present in a molecule, simultaneously bonded like this, sequentially. Okay. What is the probability of all the 3 to be carbon 13 now? Up to this we know, 1 in 10,000. Now another 1 in 100% you are tired. Now joint probability is 1 over 100 into 1 over 100 into 1 over 100 is even small. 0.501331 turns out to be nearly 1 in a million. 1 in a million. Remember, for all the 3 carbon to be seen in the state of carbon 13. Even more difficult. Even 2 carbons itself in carbon 13 is 1 in 10,000. That was difficult. Now is 1 in million. Extend the logic. In some of the molecules, you come across several carbons in a chain. In a polymer, you have a lot of carbons will be there in a chain like this. I have taken an example of 6 carbons because up to 6 we know 1 in million, and now another 1 in million. So 1 in 10 to the power of 12, 1 in a quadrillion. Probability of all the carbon, 6 carbon, to be present in the carbon 13 state is 1 in a quadrillion. Can we think of that in a realistic situation? Impossible. Very, very difficult or practically 0. So in a given molecule, all the carbons present at a time in the carbon 13 state is practically 0. You understand? The question is, how do we detect carbon-13? Now we'll go ahead further. I'll stop for the day. I'll come back tomorrow. I'll tell you more about how we get carbon-13 spectrum in spite of the fact abundance is low and probability of seeing all the carbons in the carbon-13 state in a big molecule is so low or practically zero. So we'll meet tomorrow.